Welcome to a special edition of Chemistry 112. Now, I'm not going to be doing this live stream. I'm doing this recorded because I'm currently occupied right now. So we're just dealing with this, starting off where we left off in Chapter 18, looking at this. So we're going to keep this, and as we come upon clicker questions, we'll deal with them in an unusual way, meaning that we're going to go through 3 clicker questions today. And as we go through, obviously you can't reply to them in real time. But if you watch this video and send me an email with your 3 clicker question answers before Friday's class, I will give you the points for them. So that means people who usually don't keep up with the class and have a chance to still get some clicker points. With that in mind, let's continue on with the class. So we had last left off on the idea of entropy in the second law of thermodynamics. So second law stated that, the first law, reminder, stated that matter can neither be created nor destroyed, and that's how we get that internal energy is the sum of all heat and work, among other things. Well, the second law states that any spontaneous process, so a process that occurs without outside intervention, results in a net increase in entropy for the universe. So we're going to label that entropy as a variable of S. We said internal energy was U, said enthalpy, heat energy, was H, or we're saying entropy is S. Now, what is entropy? Entropy is a measure of randomness or disorder within a system. The idea being that as things get random and disordered as time progresses, anytime that there is something that happens on its own, it's going to result in a net increase in entropy. That's where we left off last class. So how can we imagine entropy in terms of a chemical reaction? In a chemical reaction, entropy is a probability that a molecule will be acting in a certain way, in a certain place, at a certain time. Essentially, if we look at it, just helium atom in a 1 by 1 meter square box, that atom can be bouncing around at any location based on its size. As we start putting more and more atoms of helium into that box, they could be various degrees of mixed up. And that's just considering a single round spherical atom. Now, if you start making molecules, like multi-atom molecules now, as well as moving around, translating, and rotating, they can also be stretching and bending. And so we have all sorts of different possibilities, probabilities of what the molecules will be doing. Now, these possibilities could be labeled as a microstate, constant W. A microstate, how many microstates can this molecule, or these 50 molecules, or these 1,000 molecules exist in? Well, there's a way to physically calculate the entropy for a given molecule. That Kb, which is our Boltzmann's constant, which is our ideal gas constant divided by Avogadro's number. Kb is equal to the natural log of the number of microstates. So as you get more and more microstates, you can get more and more entropy, more and more random, as it will work. But what this is going to mean is that entropy is directly calculable. Now, will we ever actually calculate entropy directly this way? No. It's too big of a pain in the ass. However, we can calculate entropy in this way. So with that in mind, entropy has an absolute value we can calculate. Now, first clicker question. So don't overthink this. Clicker question 1. According to the second law of thermodynamics, spontaneous processes always result in an overall increase in what? Is it an increase in enthalpy, increase in temperature, increase of kinetic energy, or an increase in entropy? So feel free to go back and check. This should be easy points. You're not timed, you can't accidentally hit the button and send this off and get this wrong because of you bumped the clicker. So take your time, answer this. This is the first clicker. Now, this will lead us into the third law of thermodynamics, though. The third law states that entropy of a pure crystalline solid at 0 degrees Kelvin is 0. There is a 0 entropy value, but it is at absolute 0 Kelvin. So let's think about that. Entropy is temperature dependent because atoms will move as temperature increases. There will be greater amounts of movement at greater temperatures. So even though a solid looks stationary, it is vibrating. If it has any temperature in it, if it has any heat in it, it will vibrate on an atomic level. Even though it looks stationary, it's still kind of like shaking back and forth. As you approach 0 Kelvin, this motion will slow till at 0 Kelvin, it will absolutely stop. Now, if it's a pure crystalline solid, a solid without defects, there is only one possibility for the arrangement. And if there's no motion, there is only one microstate this atom can exist at, which means W would be 1. Now, if you take the natural log of 1, this is equal to 0. So a constant times 0 will give you 0, meaning there is an absolute entropy for a system. But that also means all compounds and all pure elements will have an entropy value associated with it because of this. When we dealt with enthalpy, heat energy, we said all pure elements, we're going to say those are 0 enthalpy. But with entropy, there will be a value of entropy for oxygen gas, the same as lithium solid, the same as like bromine liquid. All of these guys will have an entropy value associated with them. So we have to take them onto account. Now, how will we calculate entropy? It's just going to be the sum of all the products minus the sum of all the reactants. You don't need to overthink it. It's the same thing we did when we calculated entropy back in General Chemistry 1. Now, when this is done at 1 molar concentrations, at 1 atmosphere gas pressure, and at 298 Kelvin, we say this is standard molar enthalpy, and we give it the S naught, S circle, S whatever, like degree sign. This is telling us that it's done under standard state conditions, so I can compare this to any other scientist all around the world. Done under similar conditions, we can compare our values and know we measured it the same way. So now, so this is basically calculated the same way as we did delta H naught. The only difference is there's almost no 0 values for these calculations. Delta H, we could ignore pure elements. But entropy, we have to consider everything. So let's calculate this. So what's the entropy of these two reactions? N2O4 breaks down into 2 NO2s. Zinc plus hydrochloric acid dissolves to form zinc ions and hydrogen gas. So let's look at that. So okay. So let's do the problem 1 first. For products minus reactants. As we look at that, you'll notice one thing already off the bat. The amount of the entropy associated with N2O4 is larger than the entropy associated with NO2. because a more complex molecule has more entropy because it's going to have more microstates possible. However, there's two molecules of NO2. So even though N2O4 is greater randomized molecule by molecule, NO2 is, you know, N2O4 is more entropy because it's more random of a molecule. The net effect is going to be positive entropy when it breaks down. There's two molecules, no matter how complicated they are more complex than one molecule on the same type. So the net effect is positive 175.8. Now the units of this is joules per mole Kelvin. Joules per mole Kelvin. Now this one's a little bit harder and a little bit weirder, and we have to deal with this as it is. Products. We have 130.7 for hydrogen and negative 112.1 minus zinc, which is 41.63, and hydrogen, which is 0. Now you'd think, oh, hydrogen ions in water, wouldn't that be more random? Zinc dissolved in water, wouldn't that be more random? Well, it turns out no, because water would normally be floating around in a certain way, and then when you put zinc, when you put an ion into water, it's going to actually decrease the randomness as the water has to hydrate it. It has to surround the zinc and dissolve it. And so the degree of hydration results in a net decrease in entropy. The water has limited freedom. And so even though the zinc part makes it more random, the water hydration makes it less random. And so we see a net decrease in entropy when we dissolve zinc in there. But so let's say 130.7 plus a negative 112.1. So the products are positive 18.6. But the reactants are 41.63. So the difference is negative 2303. So negative 2303 joules per mole Kelvin. So the net effect of this is a decrease in entropy for this system. A decrease in entropy for this system. This reaction will still happen, as we'll see. This reaction will still happen and it still be spontaneous, and we'll discuss why that is, even though the entropy of this system is decreasing. Okay. But before we get to that, clicker question 2. Do not overthink this. There are 3 substances on this table. We only need 2 of them. So calculate the entropy change for this reaction. 3 moles of A2 goes to 2 moles of A3. 3 moles of A2 as a gas goes to 2 moles of A3 as a gas. So you'll figure out the difference, the change in entropy between 3 moles of A2 and 2 moles of A3. Products minus reactants. That is clicker 2. So send an email with clicker 1, clicker 2, and clicker 3 all together. Send them separately. I will hate you forever. Okay, so when we talk about the entropy of the universe, it is made up of 2 parts. Entropy of a system, entropy of the surroundings. When we look at a reaction, typically that's the entropy of the system. Everything else that surrounds it would be considered the entropy of the surroundings. And remember, the second law states that the entropy of the universe will always increase for a spontaneous process. So even if the entropy of the system has gone down, if the entropy of the surroundings has gone up by a larger amount, we see a increase, we see a total increase in the entropy of the universe. Now, when we dealt with enthalpy, the enthalpy of the system typically had a very little effect on the overall enthalpy of the surroundings, because when we're trying to heat up the surroundings, it's a much smaller effect. If I light a campfire in the forest, as long as it doesn't result in a whole forest fire, it's going to heat up the surrounding area on the cold night, but it's not going to warm up the whole forest. The whole forest temperature does not change by any significant amount. With this, and even though the energy flows into the forest temperature does not go up by like more than a fraction of a percent, if anything. So such a process would be said to be isothermal, meaning iso, like isosceles triangle, meaning the same, thermal meaning heat. So it's an isothermal process, which it will occur without changing the overall temperature. So as this heat flows into the surroundings, this is going to result in randomness of the particles. As they heat up, they are going to move faster. Remember when we looked at ideal gases and looked at how they will move and effuse greater at higher temperatures. The root mean square speed of a gas. Well, that has to do with entropy. So if I look at the entropy of the surroundings, how fast is the air moving on the surroundings, we can look at it as a function of the heat given off by the system over the temperature. Meaning if the gas is already hot, a little bit extra heat will have a lesser effect than if the gas is cold. Heat up a cold gas, it moves a lot faster and has a much greater effect than if you heat up a hot gas. So we're going to figure out our delta S surroundings as a function of the negative delta S system over the temperature in Kelvin. And so if we figure out the delta S system and the delta S surroundings, we can find the delta S universe without a problem. Now, here's an actual problem. So step one, we have to calculate the delta S system and the delta H system, where we should know this reaction will happen. Silver nitrate plus sodium chloride result in the precipitation of silver chloride solid and sodium nitrate hanging around. So let's calculate our S. Products minus reactants means we're going to take 96.11 plus 207.0, and we're going to subtract 220.37, added on to 115.5. Products minus reactants, so 96.11, 207.0, minus 220.37, minus 115.5. Already we kind of have a problem. The total entropy here, entropy of the system, is negative 32.76 joules per mole Kelvin. And that should hopefully make sense, that when I have two ions in solution, which are semi-random, and I make a solid out of those ions, the solid should be hypothetically less random than a solution. May not always be the case, but it should be. But let's calculate our enthalpy. So products, negative 127 and negative 446.2 minus our reactants, which is negative 107 and negative 407. So negative 127, negative 446.2 minus a negative, so it's plus a positive, 100.7 and 407.1. So the net effect is negative 65.4 kilojoules per mole. Note this is kilojoules, not joules. Kilojoules, not joules. Now that is so what this means is the entropy may decrease as it precipitates, but the enthalpy is exothermic reaction. It heats up the solution because when it's mixed together, it forms heat. So we're going to say S of universe is equal to negative 32.76 minus a negative 65.4 over our temperature. Now, our temperature, in order for these to be in the same units, that's 32.76 joules per mole Kelvin. So our temperature has to be in Kelvin. So 273 plus 10 is 283 Kelvin. But because the units have to be the same, kilojoules need to be converted into joules. So that needs to be times by 1,000 to turn that into joules. Negative 32.76 plus 65400 divided by 283 gives you a sum of 198. So this fits with what we know. This fits with what we know. This reaction is spontaneous. It is not spontaneous because the entropy increases. It's spontaneous because it produces a lot of heat when it does that. So even though that zinc dissolves into acid and produces hydrogen gas, even though the entropy decreases, the heat of that would be increases, making that a spontaneous reaction. So this is going to give us to our main concept of this chapter, which is Gibbs Free Energy. Based on a mathematician, Gibbs, trying to quantify what the spontaneity. How do we quantify how spontaneous this is? And so he created a new concept, the Gibbs Free Energy, capital G. This will still agree with our second law of thermodynamics, that the spontaneity, for a spontaneous system, we're going to have an increase in entropy of the universe. But so the equation for calculating Gibbs free energy is delta G equals delta H minus T delta S for the system. Now, what is the advantage of this over the delta S universe? Delta S universe wants you to consider the system and the surroundings, and this one just really has you look at it in terms of system. So it's sometimes a little bit easier to think about. But delta G's units is kilojoules per mole. Delta H's unit is kilojoules per mole. Temperature must be in Kelvin, and S, our entropy, is in joules per mole Kelvin, which means usually something needs to be converted from joules to kilojoules or kilojoules back to joules. So keep that in mind. The one chief difference, you notice this is H minus T delta S, and this is S minus H over T. That we're minusing something different in each of these guys. But so what this is going to result that for a situation where S of the universe increases, delta G is negative. Delta G is negative. So we're going to look at mostly negative delta G's. So looking at the terms of negative, when delta G is negative, we consider this a spontaneous reaction. So that means this reaction is a forward proceeding reaction. It wants to go to products. If I look at methane and I light a match, it will burn, and it will keep burning so long as I have methane. It will keep producing products. Now this, note, you still have an activation energy barrier. Without that match, methane will not burn. You need to start it. You need to put that energy, but once it produces the energy, it will keep going, keep going, keep reacting so long as there's reactants to react. So when delta G is negative, it proceeds forward. A large delta G means it's way more spontaneous. A small delta G means a lot less spontaneous. But so more negative means more spontaneity. But however, delta G does not mean speed. Delta G has more to do with equilibrium than it has to do with kinetics. So just because we have a delta G that's negative doesn't mean it's going to happen quickly. We're going to look at probably like conversion of diamonds to charcoal. That is a spontaneous process. However, that's a very, very slow process, meaning thousands of years, if not millions. So we don't have to worry about that reaction. Now the opposite, if delta G is positive, it's a big number, a positive number, this is a non-spontaneous reaction. So it does not want to go forward. Means the reverse reaction would proceed without work being done. So for example, like a weak acid will not dissociate very much unless you do some work, like add a base. If you add a base, it suddenly will become spontaneous. But will acetic acid naturally dissociate the products? No, not very much, not based on the delta G. So we've looked at negative delta G, we've looked at positive delta G. Well, delta G so what's between negative and positive, and that is 0. When delta G is at 0, it means it's neither product favored nor reactant favored. It's neither going to go forward nor reverse. It's at equilibrium. It can go backwards, but it's also going to go forwards at the same ratio. That is the definition of equilibrium. So as a reaction proceeds, as it goes forward, delta G is going to get less and less negative until it approaches 0. We're going to see so if this is negative Y and going eventually approaches 0 and stops. It's going to hit equilibrium. So this is the last thing we're going to cover today. Yes, I'm calling the class a little short, but I don't want to get too far into this. This is already kind of half the notes. So this will give us a chance to ask some questions on Friday. But this last clicker question, clicker 3. For a system with a positive delta G, so delta G is greater than 0, how will the reaction proceed when we start this from standard conditions? Is the reaction at equilibrium? Is this spontaneous in the forward direction, so going towards products? Is this spontaneous in the reverse reaction, going to like an earlier reactant, going backwards? Like if you have an acid-base situation. Is the reaction spontaneous in both directions? So which way is the reaction going to head? So remember, send me an email with your 3 clicker questions. Send it by Friday morning, and you should get the points. With that in mind, I'm going to go ahead and leave you with this for today. We're about halfway through with this chapter. It's going to get a little bit trickier, but not too much worse. I mean, as long as you can calculate delta G, delta G by saying calculating delta H and delta S, shouldn't be too bad. You have to watch out for some units, joules to kilojoules and what have you, but it's not overly hard. Okay, leave you with that. Good day. So this has been the Chemistry Cowboy. Once again, if you like what you see, please like, please subscribe. I'll be posting more videos to give you the education you need. And I've been asked to put this disclaimer to Bethel students. Remember that the log and the online learning guidelines remain in effect while interacting with any type of instructional materials / sessions. That over and out.